Hello, everybody. Welcome to the final session of Dive into AI. We're just going to wait a minute here just so everybody has a chance to trickle in, but we're so excited to have you join us today for the final session here. Alrighty, hello everybody. Thank you for joining us. We're just waiting a couple minutes for everybody to file in. Hope everybody's having a good day so far. Alrighty, guys. Hello, welcome to Dive into AI. This is session 3, AI case studies. My name is Shen Malloy, and I will be your host for today. I would also like to introduce my fellow workshop organizers at CUSE Atlantic. We have Shayla Fitzsimmons, who's our executive director, Alexi Bakadas-Westcott, who's our engagement specialist, Alex Johnston, our AI training lead, and then we also have a bunch of people joining us here on the panel, which I will introduce in a moment. But first, I would like to begin by acknowledging and respecting the First Nations, Métis, and Inuit peoples on whose traditional territories CU's work is conducted across Canada. We strive for respectful relationships with all Indigenous peoples as we search for collective healing, true reconciliation, and honoring these beautiful lands and seas together. I am coming to you from Chipuktuk, otherwise known as Halifax, the traditional and unceded territory of the Mi'kmaq. Sorry, let me just close the Zoom window that just popped up and took over my screen. All right, here we go. So before we get started, I do have a couple housekeeping items to highlight for you all. We will be monitoring both the Q&A and the chat box today. You are welcome to use the Q&A to ask questions to the panelists and use the chat to connect with each other or the other attendees or with us. Today, this workshop will be presented in English, but if you need it, Zoom does offer live captions and automatic translation features that you have the option of turning on or off, which is just located down here in the control panel. You can set the caption and the translation language to that of your choosing. Please note that this session is being recorded and will be shared through our social media channels and on our website to be used as a public resource in the future. But if you have any questions at all about the session or are experiencing any technical difficulties, you can absolutely reach out to us, connect with us over chat, or you can send a quick email to info@cuseatlantic.ca. So we have a great roster of case study presentations for you today. First, we're going to hear from Sue Malloy at Glass Ocean, which is an organization dedicated to eliminating greenhouse gas emissions in the ocean using engineering and scientific expertise. Then we're going to dive into a series of lightning talks from our Building Bridges partners. We have Spencer and Simon, who will be giving a lightning talk, and then Will, who will be diving a little bit more deeper into his work. They will each be presenting about their work contributing to the Building Bridges project. And then finally, we have Lindsay Abrams from the National Oceanic and Atmospheric Administration in the US, who will be speaking about her work leading machine learning for quality control of tide gauge observations. So without further ado, our first case study comes from Sue Malloy. Sue is the president of Glass Ocean Electric. She holds a PhD in naval architectural and ocean engineering from Memorial University. Glass Ocean is seeking ways to electrify marine vessels to reduce emissions during operations and provide vehicle-to-grid opportunities. Sue has led extensive industry and academic research papers in electric boats and tidal power and has served on numerous boards and advisory committees and standard bodies for marine renewables. So without further ado, I will now pass it off to Sue.
Thank you, Shen. Can you give me a thumbs up that you can hear me? Perfect. Thank you very much. All right, next slide. Lovely to be here. I appreciate this. I'm not feeling 100%. I've got that virus that's going around the country right now. So I'm going to try and keep it succinct. As Shen mentioned, Glass Ocean Electric has two products. We make electric propulsion systems so that vessels can convert to electric propulsion. We do an all-electric system that is put in parallel with an existing diesel system, so it becomes a hybrid parallel system. And then we also have an AI-enabled navigation system called Performarine. This system I'm going to talk about today because that's what we use our AI for. This system also helps optimize our electric propulsion system. So next slide, please. Okay, so this is an example of the data that we had to start capturing when we started thinking about electrifying vessels. So when we think about electrifying a car, we know that the average person lives somewhere around 27 kilometers from work, that they go to the gym, they go to their kids' basketball game, the grocery store, they do all of these different activities. So we've got a pretty good sense of what is needed for a battery capacity and motor capacity in order for people to be able to run their full day. But when we started looking at boats, it wasn't clear what information or what power they used. We didn't have that information generally as an industry. We didn't know the details of their operations. We just knew that for the most part, a lot of boat operators, particularly fishers, will often put very large engines on their boat. And we don't know, we suspect that they're unnecessary in a lot of the situations, but we couldn't, we didn't have the data to back that up. So what we started doing was collecting data. We started looking at vessels and we developed a proprietary mobile data acquisition system that we could leave on vessels and comprehensively gather the data that we needed to be able to understand the operations of a vessel. So in the top right hand corner is the port. This happens to be a fisher in this case. We work with fishers, tour boat operators, port boat operators, work boat operators. We focus on work boats because they go out every day or almost every day. They go out on a predictable schedule, and that allows us to be able to claim reduction in emissions. If we go recreation, it's too uncertain. So that's why we focus on work boats. So this boat goes out from the top right down to the squiggly lines, and those are lobster pots. So they transit out to the place where they have their lobster pots deployed. Then they'll check their pot. They'll go to the next one. They'll go to the next one. They'll go to the next one. So they spend about 30 minutes transiting. They spend 5 to 6 hours going around their pots and then 30 minutes transiting home. So next slide. So what this looks like from a power point of view is they drive out at about 110 kilowatts. And then they slow down. The negative down there is simply reverse. It's not negative power. So they reverse to slow down to their pot. Then you can see that they stop at their pot. They check what's in there, and then they go to the next pot, and they go back and forth. And you can count how many pots that they go to, and you can see that they do approximately 100 kilowatts on the way home. So there's a difference there, probably due to the tide or something like that. So when we calculated this, we're like, okay, we can calculate this green box in the middle. This could be their electrification part. This is their electric operation, and the two pink boxes can be their diesel operations, so that we don't have to put a giant battery on board this vessel. So at the time when we started looking at this, batteries were quite large. They're starting to get smaller now, but at the time they were large. So we wanted to be conscious of the weight and the size of the battery that we would be putting on boats. So in this green box, we're looking at 48 kilowatt hours. We're like, great, now we can size our system. And we were all very happy. We had a really good sense of it. We got hundreds of hours of data from, between 20 and 30 boats. And we were pretty happy with being able to come up with some norms. But then we started looking at the data and thinking, well, hang on a second here. What if we got this data on a Monday, and then the vessel went out on a Wednesday, and the wind was in a different direction, and the wave height was different? What kind of an impact would that have? Do we have enough information to be able to tell us that? And we all know that the ocean is a multivariable environment, and it's really too complex to be able to say, if the wave height increases by 0.5 meter, your power goes up by 5%. So we can't say those sort of things. But what we can do is we can use machine learning to help us look for those patterns that we can't see as human beings. So this is a really important application of AI. AI is essentially big data. It's stats. It's looking for patterns in multiple numbers that that change with respect to each other. So this particular environment is the absolutely perfect place to be using AI. So we are measuring power, we're measuring shaft power, fuel flow, we're measuring the movement of the vessel, we're measuring emissions, we're measuring anemometer, we're measuring speed and position, and all of those values together can be combined. And when we use the IMU, the measuring unit, the inertial measuring unit, which basically measures the movement of the vessel, that's a pseudo wave buoy type movement. It's essentially, if the vessel moves more, the wave height and the wind are going to be more, and then if it moves less, it's going to be calmer, right? So these are the things that we can infer from that. So we're able to connect the operation of the vessel to the meteorological conditions through an IMU, through the anemometer, and through the fuel use. So next slide. So what we did is we started taking data that we had and predicting other data that we had. So we built machine learning models off of the data that we had, and we held out one set of data, and we use our models to predict. And what we found is that we get really, really close data, and we're really happy with what we have. We're at the point now where we have a commercial product from this. So we can have a fuel consumption difference of about 2.7%, which is phenomenal. The second trip was 1.8, and then we have a much more complex trip, and the difference was 5.7. So what this means in a practical way is, if you have could we go back 2 slides? I just want to use that graphic to show what I'm talking about here. So if you go out on this trip and you say, okay, well, what's the weather today? And you plug in your wind direction and your wave height and the timing of all of these into your routing for the day. We can tell you with our app, if you go clockwise around your pots, maybe today, because of all of the wind conditions, you'd save 10% or 20% fuel, right? So, or you could say, if you've got a choice to go out any day this week and you only want to go out 3 days, well, based on the weather conditions, if you go out Tuesday and Thursday and Friday, you'll save 20% fuel versus going out Monday, Wednesday, and Friday, or something like that, right? So you can actually use the weather prediction to help you determine how much fuel you can use, which is a really important piece. If we, imagine with all the millions of fuel liters of fuel being used every day, that if we could take an impact of 10% of that simply from information, that becomes a phenomenal potential greenhouse gas impact. Okay, so we'll keep going down to 2 or 3 slides forward. So this one here, this gives us a sense of the kinds of numbers we're talking about. So we have high waves and low winds is the blue line. Low waves and low winds is the green line. So that's the lowest one, the green one. And then you have high waves and high winds is the orange line. So you can see that there's a good 20 to 25% difference in fuel use in the upper end of the speed. Well, pretty much the whole way up, actually. In fuel use, simply due to weather conditions. So this potential, what I would consider a bit more insight into your operation. So there's a subtler piece there where you may not you may have no qualms about going out Wednesday versus Tuesday. Maybe it was just like, well, I was going to go to the Costco on Tuesday, so I didn't want to go Tuesday, so that's why I was going Wednesday, but you can move your Costco trip to Wednesday. So all of these different things can be impacting your operations, and you can now have the insight into it and see how much of an impact you can make on your day-to-day fuel use, which of course translates into emissions. So the next one, please, next slide. So what this looks like in an app is we have a hardware system and an app system. So you install the hardware system and you have the app system, and then you can have historical data. So this is kind of the starting point, is let's get used to using an app like this and getting this kind of information. So on the right-hand side, that's a graphic of what you would see in real time. And you can make your boundaries according to what you want. So in this case, we'll say that when you operate at $50 an hour, any sort of a rate of fuel use, so not a net fuel use, but a rate of fuel use of $50 an hour, you don't want to do that. You want to keep your fuel use less than that. So in this case, you can have a real-time plot, which will start to highlight when you're moving out of that. And it can give you a trip total based on your routing for the day. Right now your trip is costing you $120 and you slow down. Okay, now your whole trip's going to cost you $80. So you can have all sorts of different types of feedback. And then if you're a tour boat operator, if you look at the app, the first graphic where you see the different bar charts, you can look and you can say, well, how is our fuel use different on different days? And suppose you have 3 boats and 8 drivers. Well, you can look and you can say, well, why is it every time Bob drives, he uses like 25-30% more fuel than everybody else? And you can find out through our app and through the information and the insight that we can give you that, well, actually, the reason Bob uses more fuel is because the prevailing wind when Bob takes the vessel out is always in a certain direction that causes him to use extra fuel. Or you could look at it and find out Bob needs to go get some retraining on his driving. So this is the sort of insight you can get. And you could have extra insight over time. You can say, okay, well, we choose this route all the time. Now we're seeing that if we keep going this way when the wind is in this direction, it actually costs us more in fuel than the money that we're earning if we have 10 passengers. So you can start to optimize your operations, and you can choose your routing based on your costs, so that every trip that you put out there for the most part is at least break even. And I think that's the last slide. Maybe the next one. Yep, so that's it. So we have we've got electric propulsion. We've built this AI-enabled navigation system. It's got a lot more applications. It collects data that we can use for autonomous vessel training. It's beyond the horizon information for the defense industry. There's a lot of data in there, but essentially the way that we describe it to people who don't understand it is it's a Fitbit for the boat. And when we started using Fitbits and counting steps, we started collecting big data that helped everybody. So now we know that certain communities, people don't walk as much, and maybe urban planners need to add pathways there, right? So the big data that we get from this helps the wider industry and stays anonymous. So that's me. Thank you, Shen.
Excellent. Thank you so much, Sue. Are you okay to stick on just to answer a couple questions?
Yep, not a problem.
Oh, yes. If you do have any questions for Sue, you can direct them into the chat or into the Q&A. I see one coming in from Jaden. How generalizable are your models? Do you need to retrain or fine-tune for every single ship installation?
So not for every ship, but we have a general model, but we're finding that we need to class it. So very large ships will have one model, smaller vessels will have another model. And we also, our plan to go forward is we have a generic model that we I don't want to say customize, but we personalize for each vessel once they learn it, once they use it. But you can get an awful lot of information just using the generic model. You're getting over 80% accuracy on the results with just the generic model.
Excellent. And just curious, how much data was required to train your model?
So you need hundreds of hours of data for every single model. So between 300 and 800 hours will get you a beginning model.
Excellent. And then we just have one more from an anonymous attendee. Do you charge the vessels for using the AI app?
So we are just getting started on that. We've got a beta release right now that we're out there using with vessel owners. So the plan is to make it it's going to be a SaaS product, but it'll be like a cheap or freeware version, and then reporting and different depths of insight will come with cost.
Excellent. Thank you. We do have to move on, but if you do have any other questions for Sue, you can absolutely direct those into the chat. But to kick off our next series of Building Bridges presentations today, I would like to introduce Spencer Bialik from Ocean Networks Canada. Spencer is the machine learning / AI specialist for ONC, and he will be presenting their work on detecting anomalous hydrophone data using self-supervised learning.
Cool, thank you, Shen. And hi, everyone. I'm very excited to be introducing you to some of the work I've been doing at Ocean Networks Canada over the past few months, trying to automate the process of detecting when our hydrophone data is of anomalously poor quality. Next slide, please. So this is the situation we have. Ocean Networks Canada has a large network of hydrophones on the ocean floor recording sound, which then gets converted into these visual representations of sound called spectrograms. Most of these spectrograms are perfectly normal, but occasionally there are anomalous spectrograms, which usually result from a variety of instrumentation failures. We get things like tonal features, data dropouts, data gaps, sensitivity issues, and of course, the dreaded category of unknown anomalies, types of anomalies that we haven't even characterized yet. At the moment, all the work in identifying these anomalous spectrograms is done manually, which is sometimes a lot of work. So I'm currently working on a way to automate this process using machine learning. However, there are some problems with using a standard machine learning approach. Next slide, please. First of all, we have a very small amount of labeled data. There is a massive amount of data in general, but anomalies are quite rare. So it's difficult to manually identify enough of them to build up a sizable training data set for supervised machine learning. Traditional supervised machine learning usually requires a lot of labeled data to perform well. So this is an issue. Second of all, supervised machine learning methods perform well on data in the same domain as their training data. But like I said, we have unknown classes of anomalies which won't be in the training data. So our ability to detect these anomalies could be negatively impacted with traditional machine learning. So it's not looking good for supervised machine learning. Luckily, there is potentially a solution. So next slide, please. Self-supervised learning is a very exciting branch of machine learning that is able to learn information from a large unlabeled data set by creating supervised tasks from the data itself. I mean, these tasks can be things like masking a patch of an image and asking the model to reconstruct the missing patch, or taking a few patches from an image and tasking the model with predicting the correct position of each of them. By giving a model these self-supervised tasks, it incentivizes learning about the structure and properties of the underlying data set, hopefully learning meaningful features in this first pre-training step. You maybe didn't know this, but you're already familiar with the technology that uses this method. Large language models like ChatGPT are trained by providing a sentence or part of a sentence, masking or removing the last word, and tasking it with predicting what the masked word is. By doing this millions of times, it learns the inherent structure and semantic meaning of language and can later be fine-tuned for specific tasks. And that is the second step of this two-step process. Next part of this slide, please. So once you've pre-trained on a large unlabeled data set, you then have a model that understands something meaningful about your data. So it's already got sort of a head start when you want to fine tune it on downstream tasks. For language models, this might be translating between languages. In our case, with spectrograms, we have a small set of labeled data, which we can train the model to predict if a given spectrogram is anomalous or not anomalous, a normal spectrogram. So it's a simple supervised binary classification setup. next part of this slide, please. So this helps to reduce the need for large-scale labeled data sets. This image on the right comes from a paper in which researchers were trying to identify specific features in medical images. It shows the performance of supervised and self-supervised models as a function of the fraction of data that is labeled. So in the region that I've highlighted, where little data or very little data is labeled, you can see a large performance increase for the 3 self-supervised models, the top lines, over the supervised model, which is the line on the bottom. And yeah, this is the region where we are with spectrograms. So we could potentially see a lot of performance boost in this area. Next part of this slide, please. One of the most compelling reasons to use self-supervised learning is its ability to generalize well to data not in the same domain as the labeled data. A paper from last year, which was looking at a very similar problem of identifying anomalous spectrograms, but using radio astronomy data, showed how useful a self-supervised model is when tasked with identifying anomalous spectrograms, as more and more types of anomalies were removed from the labeled data set. Even when 7 of the classes were removed, which was most of them, it could still identify most of the anomalies, and it saw a massive improvement over a supervised only method. So these are all the reasons why a self-supervised approach to anomaly detection is going to be used at ONC, and I already have some promising results. Next slide, please. This is very much a work in progress still, but the method seems to be working quite well at identifying anomalous spectrograms. The metrics we are getting on the test set are very impressive as well, with 97% of known anomalies being found, while the precision in its predictions is also quite high. Keep in mind that these metrics may change a lot as this project continues, but we are seeing some pretty good numbers right now. And last slide, please. So yeah, this was just a very brief teaser about this method with only a few results so far. So you'll have to tune in to the next workshop next year, I think spring 2025, to see how ONC is going to be using this method to drastically reduce the amount of work it takes to manually check this data and ensure high quality hydrophone data. So thank you.
Thank you, Spencer. If you have any questions at all for Spencer, you can direct those into the Q&A. We have one from Dwight Owens for Spencer. Once the anomalies are identified, what happens next?
That's a good question. I think we will potentially leave that up to the users. We will probably have flags in Ocean Networks Canada to let people know that this is potentially poor quality data and you might not want to use it.
For sure. All right, we do have to, oh wait, one more here. How do you differentiate signals from noise, problematic sound? Say if marine mammal calls exit in your sound data. Signals, oh, sorry about that. How do you differentiate signals from noise? So if a marine mammal calls, how do you differentiate that?
Right. So currently, we're not differentiating that at all. We're just looking for when data kind of exists outside of the normal domain. And that's just the first step. There are going to be other steps we implement that probably use a supervised learning approach to then classify each of the types of sounds. So we'll know, we'll be able to classify the true bad data, the bad anomalies from the interesting anomalies, which are the marine mammal calls.
Gotcha. And then are you planning on modifying or correcting any of that bad data detection?
I don't think that's in the current plan. I think we want to just leave the data as it is, and if the end user wants to then clean it up themselves, then they have that option.
Perfect. Thank you so much. All right, we do have to keep chugging along here. So our next Building Bridges lightning talk comes from Simon Boulever, who is the data scientist from the St. Lawrence Global Observatory. And Simon will be sharing about leveraging AI for data and metadata extraction.
Hello, everyone.
Oh, you got some feedback.
Yeah, excuse me. I think it should be
Oh,
resolved
there
now.
you go. That's better.
Thank you, Shen. I'm happy to be here today to share with you how we're using AI at SLGO. First of all, at SLGO, it's a kind of different organizations to some other ones. We don't produce data, so we work with data suppliers, with scientists, with organizations, and we collect their data, and we work to standardize it and share the data to our portals, data catalog, and applications. So what we are and all is we are a big ETL, we're a big pipeline. So next slide, please. Okay, so there you go, there you see it. So basically going from left to right, you see we collect the data from, like I was saying, the data providers, and we extract it, transform it, load it into our different catalogs, visualization tools, Atlas, and so on. So this is really our core activities. Next slide, please. Why we need to innovate, why we need to bring AI into what we do already into our world? Well, with the growing numbers of data catalogs available, staying competitive and securing funding has become increasingly difficult over time. It means also staying relevant, having a different excuse me, I'm stepping on my toes here. Differentiation factors also is becoming increasingly difficult. At the same time, the volume of data continues to surge, requiring more resources and manpower to manage this data effectively. So all in all, innovation is thus essential to streamline the processes, reduce manual effort, and ensure we remain a leader in this evolving landscape. Next slide, please. So how can we use AI within our organization? We see it in, well, there are probably more ways, but we see internally, we see it in 4 different ways. The first one that everybody knows is about using AI for personal work. So everybody knows ChatGPT, Microsoft Copilot, Grammarly, for example. We can also integrate AI functionalities into our different applications, such as having an AI-powered search bar, for example. So this is something Swiss Atlantic is working on, for example. We can also unlock the full power of AI by making sure data is AI ready. So at some point in time, if somebody wants to use our data that we have into our catalogs to train an AI model, well, our data needs to be of good quality. So by following FAIR principles, we turn data into high quality data, and it brings a strong foundation for to train AI model with. Last point is we can also use AI to enhance the efficiency and experience of our internal processes. So being a big ETL, we can break down all those chunks into sub-chunks and sub-chunks and find ways to basically bring innovation. So an example, well, we can change slide. I'm going to give an example for the details. So as you see here, there's a lot of boxes and text. But this is our vision to automate and bring AI to our work, to our daily activities. So the process starts with a manual. Well, as it was done several years ago, we would start by manually extract metadata from the various documents that we have. We have all kinds of different data, and then we would transform the data manually and validate it manually. Over time now, we aim to reduce this manual work by introducing AI and in this whole process. So in the metadata and data extraction and transformation and validation. So this phase approach is going to help us maintain good data quality by, in fact, increase data quality and make our work more efficient. Next slide, please. So building on what I was just saying, the app we're building right now is designed to change how our data integrators handle unstructured documents. So by simplifying the process of summarizing documents and extracting both metadata and key data points, we empower users to efficiently process large volumes of text. So unstructured documents, as you see in this table here, often hold untapped value. So if we have a PDF file that has 100 pages, it's going to be tough or difficult for a data integrator to go through all of it and get really all the value out of it. So by using AI, we aim to really able to take out all the good value from those documents and be able to bring it in a structured way into our data catalogs. Next slide, please. So this is a really high level, of course, but our app will transform unstructured files, so PDF files, Word files, into structured outputs through an AI-driven pipeline. So these outputs will look like formatted JSON files, for example, with keys and values. And we will be able to get those JSON files directly into our catalog. So really the goal is to enhance all our processes, the way we do stuff internally, and be able to treat and transform and disseminate more files, more data sets. Next slide, please. So here's an early visual of the app we're developing. We're still in the very early phases where we're testing with different models, prompts, and so on. But this is what a user would see, for example. So the user would upload this file to the web app, and then the app would automatically extract metadata and data fields such as a summary or creation date or various stuff like that. And then the user will be able to change those fields if need be, and then download in the end the metadata under the format he wants. So, for example, a JSON or anything else. So that's it. So there's still a lot of work to do, but this is what we're aiming for the next few months. And that's it.
Perfect. Thank you, Simon. If you have any questions for Simon, again, you can toss them in the chat or in the Q&A. Don't see any coming in at the moment, but Simon, I was wondering, what do you think is one of the most important things about engaging with AI?
Good question. Can you clarify your question a little bit? I'm not sure I understand the
Well, it's all a new field. So what are some considerations or maybe some best practices or tools that you're using when building this model?
Yeah, well, before trusting the output of the model, you need to make tests, to make sure that what the model outputs makes sense to what you intend to receive, for example. So that's something we think is very important. So when we start testing with our data integrators, we aim to make sure that the process is very thorough and we fine-tune the model to get the proper results.
Excellent. And then we just have one coming in from Jonathan. How are the early results looking with the translation factor of the extraction process? The bilingual aspects has always been a challenge for CUs, as we all know, but I imagine it's complicated when using AI. Is it safe to assume that ChatGPT is the large language model?
Yeah, this is right now we're using not ChatGPT, we're using the OpenAI API, in fact, but it's the model behind is the same. Well, there's a variety of models, but they are the same models. And regarding the question language, right now I don't. The first documents we're testing with are French documents, but there doesn't seem to be any difference in accuracy between French and English so far. So it's something we're also looking at because we need to, let's say we extract data and metadata from a French document. We also need to port it in and have the metadata translated. So it's something we're looking into.
Excellent. And then just one more in the chat. What is the difference between the automated metadata extraction from the template versus the actual AI method here? And how do you make sure that the AI extracts are correct info?
Good question. So basically, with AI, with some AI models, you can when you interact with them through APIs, you can ensure that the output is structured. So this is what we do. We ask the model to answer in a very defined way. So hence the metadata schema that we use at CUs. So we do that. And what's the difference? So the prompt we're making is very thorough, and most of the instructions in it are kind of the same questions the user using the metadata entry form sees. This is what we ask the model to answer. So the model receives the content from the PDF or the Word document. And in its prompt, it's reading all the same, pretty much all the same instructions as in the metadata entry form, and tries to answer them as best as it can. So the last step regarding the accuracy, well, that's a good question. We have the data integrator in the loop, so that's how we tackle this question. We basically each document we will process. Well, the end user will need first of all to confirm that the data is good, and one way we're thinking about improving this or helping the data integrator with is to show in the document where is the source of the information. So yeah, so that's how we aim to do it or tackle this question at the moment.
Right on. And then an easy last question. How many people are on the team doing this work?
As developers, we are two so far, and we're a small team of 4 person on this whole project.
Awesome. Hey, small but mighty. That's okay.
And yeah, that's it.
Okay. So for our last building bridges specific presentation today, we have Will McInnes, who is the geospatial specialist at the Hackeye Institute, and he will be talking about using AI in mussel mapping habitat.
Thanks for having me, Shen.
There you go.
If you could just go ahead and flip to the next slide and we'll get right into it. I thought that I would just give a little bit of context. I'm with the Hackeye Institute, and we work on the coastal margin of British Columbia. This slide gives a little bit of an overview of some of the things we do. I'm in the geospatial technology team, so we support science in all these areas. We're sort of in charge of all of the machines in this image here, the drone, the aircraft, the vessel there. And what we're focusing on today is a nearshore ecology component in the intertidal. So next slide, please. And we're going to be looking at mussels. And the question is sort of, why do mussels matter? I thought I'd put that in here to start. I'm not an ecologist, not an expert in this area, but I'll try my best. They're ecosystem engineers, so they provide structure, habitat. Without them, we're looking at bare rock, basically, and they provide place for little animals and all sorts of stuff to live, food for ecologically important species like sea stars and sea otters, for example. And we've been surveying these intertidal areas, sort of specifically looking at mussels since 2016. We're a long-term ecological observatory. Next slide, please. And here, I just thought I'd show, this is Alyssa Gaiman, who is our ecology lead on this project, and showing, the typical field method, which is a quadrat, a 1 by 1 meter. Any of you who've worked in these areas know this is sort of like what is done. There's a team of them. They go out, for example, they go to 5 plots per site. They're counting individual animals. They're measuring, looking at depth. It's a lot of detail, but it's not a lot of area. So they visit these sites a couple times a year, every year in the same place over time. So it's an amazing data set, but the coverage spatially is quite small. Next slide, please. So this just sort of shows the scale that we're talking about. Here's a quadrat, and if we start zooming out, in the background is drone data. This is sort of what 5 quadrats in one site. And if we zoom out again, this area here is how much we might see sort of in one survey that takes about 20 minutes to fly. And when we're out surveying, we go out for about a week with the drones, and we have our sampling sites. We can visit about 20 sites, and the comparison of the field teams do about 15 square meters of area that they look at. And we look at, in this case, about 330,000 square meters. And another important point is they're only visiting a few key areas that they can walk to for one, or boat to, and that are safe to visit. There's a little picture in the corner here showing some of the outer sites that we can visit with the drones. And these places are just too rough and dangerous for field crews to safely go and survey. So we can cover big areas. It's different data, but it's a much bigger coverage. Next slide, please. Oh, let's flip ahead. Interesting. Okay. So how we map mussels with drones. So we're out in boats or on foot, and we fly small drones. There's a whole bunch of different drones that you can use for this. You can ask me about that if you're interested later. We fly them in a grid pattern, overlapping grid, and collect enough images that we can reconstruct in something called structure from motion software to create orthomosaics, so imagery, and also it's 3D, so it creates a point cloud. So we get not only aerial coverage, we also get elevation. So the bottom right example there just sort of shows, that the data is on a map and it's 3D, so we can get a lot of different attributes out of it. But the challenge next is, we've got a picture, it's very nice. How do we quantify how much mussels are we seeing? Next slide, please. And so the question is, why are we using AI? Okay, not just because that's the theme today, but it's quite difficult to classify this imagery using traditional methods. This is a time series here of one of our sites. One thing I noticed right away is a variety of color and lighting. And that's difficult for traditional remote sensing techniques because it's hard to say, well, we want to look at light versus dark, or green versus red versus black. We also get a variety here of spatial resolution, so pixel size. We also get a lot of blur and noise. So all the traditional techniques we tried don't really work. So that's why we're leveraging AI. Next slide, please. So I just wanted to put this on here to show a little bit about when we talk about AI, we've heard about large language models and, signal processing, all sorts of stuff. For computer vision imagery, we've got a few different tasks that can be done. Given this input image, we see, of course, a couple of dogs sitting on a rug. And there's a few things we could do. One is classification, where we just get an output that says, okay, there's a dog here. Next is object detection. So this is sort of something that's useful if you think about self-driving cars. It's, okay, I see 2 different dogs. Here they are. They're distinct individuals. Another one is instance segmentation, where you're not only, getting, this is a dog, this is another one. You're getting distinctly exactly where it is, each pixel, and also distinct individuals. And then there's semantic segmentation, which classifies every pixel in an image, what it is, but it doesn't differentiate individuals. So that's what we're doing here to look at mussels, because there's so many of them, they're small, they're covering each other. We don't want to or need to know how many or which ones, we just want coverage. So that's the kind of model we're using, semantic segmentation. Next. So how do we train the model? We've heard about training. And what we need to start with is labels. In the middle here, this little diagram showing the drawing around the mussels. That's really how it started and how we do it. And we need a lot of labels. So we have a bunch of these scenes here, which would be, a site at a given point in time. And we have folks that are doing this tracing. It takes forever. and there's no way we were going to get our archive. And that's why, through our archive, and that's why we kind of had to go through this project. So what we create is we have an image, and then we have labels on the left. And then we chop those up into little squares. We spin them all around, we duplicate them, flip them upside down, and then we can create a whole lot of tiles to help train our model. And that's sort of on the right-hand side there, with the labels flashing on and off, showing what goes into the model. And I think some folks have talked about it. We split our sets up into training, validation within the model, and then testing to see how well our model did, so we're not biasing the results. Next, please. And so I'm not the AI expert here. I'm the drone and geospatial person, but I just want to highlight Taylor Denowden here, who's sort of the one who's trained all these models. And this is sort of just showing a little bit of how the training goes. We have our known labels in our input. We have a neural network. We're using one called UNet++. And we create a model. It predicts the labels. And then we compare our predictions to our known labels. We look at the errors, and then we try again. And we keep going through like that. And that's sort of the simplified version of how the training happens. Next, please. This is just sort of showing how we track performance. I'm not going to go into all of it, but the main one we use that's well used is called intersection over union, or Jacquard similarity. It looks at comparing the model versus the labels. Accuracy is one we hear about a lot, but in an instance like this where we have a big image and only a few muscles, it's not a good metric, because if we just said that there were no muscles in every image, we would have a really high accuracy, because let's say 98% of the image is not muscles already, then we get tricked by that. So that's why we use these other ones. You also heard about precision and recall. And these are our metrics we use to help choose a model and also to help refine it. Next, please. And this is sort of showing, as we go through different models, we can compare different types of models. And of course, the performance degrades over time. We ended up, as I said, with this UNet++. Next. And so the results here, we've got flashing on and off the results. The green is sort of correct. Purple is false positive. And then there's also some false negatives, meaning the model does quite well. We have a few areas where it predicts muscles where there aren't any. And there's a few areas also that it predicts muscles that we didn't even notice, the label trainer. So that there's some of the challenges there. But since we're working in such a large area, this is still a really useful tool for us. Next slide, please. And then the output here, what we get is we can look now at muscles coverage over time. This is an example at one of our sites. If you look at some of the red, you do see quite a lot of change through time. On the left here is the graph shows, a few of our different sites that we visit. Some of the trends we see are general trends through time, environmental factors, general conditions. Some of them are, we get big changes when logs and things hit. And this just reinforces that this is a useful method, because we're seeing such larger areas compared to our few plots that are done in the field. Next, please. Some of the issues that we run into that cause challenges for us, shadows is a big one. Muscles themselves are dark and live in cracks and shadows. So we have quite a bit of error in those areas. Uncertainty is another one. So there's a lot of stuff that sort of looks black and dark. And we have a hard time telling, which makes it hard to make perfect labels. The computer has a hard time telling. And another one is, if we look at this 3D image, just a regular picture, I should say, we can see that, we forget sometimes looking straight down that it is quite a steep area. And we have, habitats living on steep walls. So we have to factor that into some of our calculations, for example, making sure to look at surface area. And also it can lead to a lot of uncertainty when we have steep walls or even overhanging areas where mussels live. Next slide. What we do see though is in some areas, dramatic large changes. So this is one rock, for example, that's one that our field team can't get to because it's quite rough. We typically have a 1 or 2 meter swell here. And just in between 2 years, we had a massive change just on this one rock that's like, let's say 15 or 20 square meters of mussels that disappeared. And so that's why, we're not as worried about the small details of areas of uncertainty. Next. And some of our future work, looking at other land cover types in these habitats. So sea stars, we're working on a project, in fact, to count sea stars, so using object detection. Another one is gooseneck barnacles are quite prevalent in some of our areas, as well as we've had other researchers interested in seaweed. So we're sort of bringing together a few different domains, because we've in fact also have a whole other kelp detector system. And so starting to get towards a holistic approach where we can take a scene and pull all sorts of different habitats into it. Next, please. One question is, how do you actually use it? How does it work? This is a very riveting video here of how the model is run. And so we have a Python package. If you want to hit the QR code there, you can get it. It works for kelp or mussels. And you can run this on your own machine to process drone data. Next. And if you want to learn how to do this yourself, we're actually going to put together another more technical workshop just on this product. So if you want to get on our list for when that's going to happen, please hit that. It hits a Google form to find out more. You can join these nice people here counting mussels on the beach. Next, please. And I just wanted to say thanks to our partners, CUs, all the folks here. We also use data from a bunch of other sources, California, Oregon, to try and train and test our model to make it a little bit more robust. So if you have any questions, please drop them in the chat, and thank you.
Perfect. Thank you, Will. We do have one question coming in for you from Dwight. Were the images on your next to last slide AI generated?
Oh, yes, absolutely. Yeah. And in fact, I had to have the AI teach me a little bit about AI because I'm not the expert in the area. So yeah, we try to incorporate it anywhere we can. I see a question. Do you want to answer this question here from Jaden?
Yeah, okay, sure. Yes. Okay, I see. How sensitive is your model to the quality of the labeled data? Do you see significant differences in how different people annotate the images? And does that make a difference to performance?
Yeah, that's a great question. It does for sure. And in fact, it's kind of one of the most important things generally is having quality labeled data. So we do a two-tiered process where we have one person label the images and another person check them over. And so that tends to help even out some of the issues of subjectiveness. And another thing is in the training of model, we don't train it to its maximum performance, because if you do that, it starts to overfit the data. It works very well for your training set. It doesn't work for other testing areas. And so that's what we're always trying to, now that we have a model running, we trying to pull in data from other areas, different habitats, because it does end up getting overfit if you use sort of too much similar imagery or labels. Thanks.
Excellent, thank you. And yeah, we can absolutely highlight your technical deep learning workshop in our What We Heard report. So we'll get that sent around for everybody for sure, for sure.
For sure, great. And I see someone's asking for the QR code. So I'll just drop, oh, thank you, put that. I can drop the links into the chat as well.
Excellent. Perfect, thank you, Will. So for our final case study today, I would like to introduce Lindsay Abrams. Lindsay is an oceanographer with NOAA's Center for Operational Oceanographic Products and Services. Her primary job is the quality control of tide gauge data. Lindsay received her master's degree in physical oceanography from Stony Brook University in New York and a bachelor's in biological oceanography from North Carolina State University. So without further ado, I will now pass it off to Lindsay.
Thank you for that. Yeah, I'm glad to be here. I think we can actually just go ahead and move to the next slide with that intro. So as was said, I work for US's NOAA, and my office specifically is known as kind of the tides and currents office. That's our primary product, our tides and currents data. And some of our tide gauge sensors are depicted on the left here. This is Sand Island out in the middle of the Pacific. And it depicts a couple of different of our types of water level sensors here. And if you hit the forward button, so that's where this station is located, and our office manages over 300 of these water level stations or tide gauge stations across the US and territories, and they are transmitting data every 6 minutes. Next slide. So our existing workflow for the quality control of this types of data, we have the data coming in raw from our primary, and we have usually two sensors at a location. So we have that data coming in. There's some very limited QC that's done basically at ingestion, just removing the most extreme outliers and some averaging. And then we have preliminary data that we are responsible for reviewing and correcting and producing a verified product from. Next slide. So these are some of the issues that we commonly see in our preliminary data that we're reviewing. I am on the team that is doing this work every month. We see data spikes, we see data shifts, flat lines. We also see things like this bottom right corner, which was a tsunami that came through the area and creates some unique signals sometimes. And this is important to consider because we don't want our model to count these types of data as bad because those are real signals. And these obviously are not unique to water level data. These types of issues happen in other data as well. So these are kind of common data quality issues that we see across many of our types of sensors. Next slide. All right, so to give an idea of kind of the scale of data quality control we're doing, this is a typical month, what a typical month of data looks like. There's roughly 7,000 6-minute data points per station per month. And if you just hit it one more time, and then once again, this equates to 2.1 million data points per month that are being reviewed by us manually. There's a team of about 8 of us that are reviewing this data and correcting it every month. So next slide. The core idea behind our project is really that we do have data sets, decades of experience quality controlling this data. And we have both the raw water level data and the verified data that humans had reviewed. So we felt like we had a good training data set for an AI model to potentially train on basically learning the patterns of how previous verifiers corrected this data and learn those patterns and apply it to future data sets. So this project, the goal is to develop and demonstrate an optimal AI approach to QC water level observations. And we wanted it to both classify the water level data from the primary sensor as good or bad. And we also wanted the AI approach to replace bad data points and fill gaps that are missing data with some prediction of water level comparable to our current protocols. And we also want this project, we wanted it to have the potential to be adapted to partner collected water level observations as well. I'm sure you guys are dealing with this, but there's a lot of low cost water level sensors going out. A lot more people are collecting their own water level data. So we feel like there's this need for help with quality control of those data sets as well. And next slide. All right, so our data and methods, we selected 57 representative stations. And if you can go back one. All right, so on the map on the left depicts our water level station network. The blue dots are the stations that are actually represented in our model. We tried to select stations that cover the region and have different tidal characteristics, different percentage of tidal contributions to different tidal types, different tide ranges, things like that. We used about 14 years of data and divided it up into training, validation, and testing with the dates listed here. We also spent a lot of time cleaning our data and scaling it appropriately. As some other people have talked about, we also have the issue of this data set is very imbalanced. We have far more good data than bad data. The breakup is about 96% good data, 4% bad. And that is something that we definitely are trying to better represent in the model. So we try different resampling methods, and we found, at least initially, that a 90-10 split was pretty good for us. That's a 90% good, 10% bad, to better amplify the bad data points, because that's what we really care about the model identifying, is the bad data points. And we tested several different AI models, such as logistic regression, random forest, gradient boosting, and neural networks. And we did land on a multi-layer perceptron neural network model. It gave the best performance. And then there's some of the details here about how we set that up, but it's pretty standard approach for a neural network model. Next slide. All right, and then here's our overall skill assessment. So on the left, I just want to clarify that we are really interested in where the data was bad and the model correctly identified it as bad. That's the real accuracy we care about. We don't care quite as much about true positives, which is where the data was good and the model correctly predicted that it was good, because that's not what our focus is on. We want this model to be able to find the bad data. So we're interested in that true negative category right there. That's depicted on the top left. And our percentage accuracy for that category, the true negatives, is about 85%, which is not bad. We definitely wish we could get a little bit higher, but that's where we're at right now. We also are interested in this false negative category, because that's where the data is actually good, but the model predicted it as bad. And we definitely want to minimize those cases, because we don't want to be flagging and removing good data. We want that to be heavily penalized. So that's something we're also trying to keep track of and minimize. And down here at the bottom is a plot of water level data for Charleston, South Carolina. And it shows some of those labels and how basically the results of the model look. The darkest points are where the data points were predicted bad, and those line up with the data actually being bad. Those are spikes, right? So those were correctly identified. I don't know if you can tell super well, but there is a gradient in color for these labels, and that is related to the predictive score. So how confident the model is that data is bad. And you can see that it was super confident in these spikes over here at the end of the month, but it's hard to see, but at the beginning, there's some that are yellow to green, and those it has low confidence in. And it does look like that was just like an anomalously high water level that day. Like it doesn't look like it was supposed to be suspect. So those are the kind of what the results look like. The ones that are kind of in between, those were false. Those were false negatives. So they should not have been flagged, but they were as bad. So those are things that we definitely want to improve going forward. And next slide. All right, so here's some examples of where the model does well. It seems to do really well with flatline data. It gets where the curvature changes and doesn't identify that data as bad, but it correctly identifies the actual flatline data as bad. That's even more noticeable in the bottom plot. It's not uncommon for us to have like intermittent flatline data. So it's like some of the data is good and follows the curvature of the tide signal, but there's intermittent flatline data. And you can see that the model handled that situation really well. It identified the data that still follows the curvature is good, and then the other data is bad. Next slide. All right, and here's some examples of model issues. So in the top plot, this was a tropical storm that came through, anonymously high water levels, and the model struggled with this. It thought it looked suspect, but obviously has some low confidence in that. These are exactly the rare events that we talked about. We don't want the model to identify these as bad. So that's something we're working on. The model also struggles with data shifts, which can happen when basically like something hits a sensor or something something goes wrong with the setup. Like a sensor can drop or shift a little bit, and that shift persists. The model definitely struggles with that. I think for the obvious reason that you need a lot of information, you need a lot of data on either side of the data point to realize that that's an issue. And right now, the way our model's set up, it's not accounting for that well. So these are issues we're working on. And next slide. All right, and so the data fill model, everything I've shown you so far is the data classification, just identifying data as good or bad. The next part of our work is the data fill model, which is using AI to actually predict what the water level data should be when it's missing or the bad data needs to be replaced. We did some initial work looking at a similar neural network type model, but the inputs were a few data points before and after the missing data, and it predicts each data point at a time, basically. It tries to predict each missing data point at a time. And initial results show it to be promising, but this is much more in the preliminary stages, and we are working on best methods here and also assessing if AI is the best approach for gap filling as well. And next slide. All right, so where we're at with this project, the past few years is more just about proof of concept. We are now in the process of trying to move towards formal, move towards operations. So we have secured funding to hire a postdoc who is going to help us with this, an AI developer to really flesh out those methods and make sure they're as good as we can get them for our operations. We're working on this with one of our ocean observation offices, the one down in the Gulf for us, and our academic partners. That's where the postdoc will be based out of, is Texas A&M Corpus Christi. We are in the process of hiring that person now to start in the spring, and we will plan to spend the next year or so with AI model development with this postdoc. We do plan to test on partner data about a year or so into the project, just to make sure that our approach is also working for external partners as well. And I do want to plug, I know you guys are mostly in Canada, and that's technically outside our region, but if there's stations or water level data that's kind of nearby some of our areas, I definitely would be interested in that down the line. And our ultimate goal is to start transitioning this to operations by spring of 2027. And this will be our first AI project that we will be transitioning to operations in our office. So we have our work cut out for us, but we feel that this could save us a ton of time and be very useful for our partners. All right, and next slide. All right, we wanted to include this. I felt like this could be important for this group. some things that we really are thinking about with how to transition our first AI project to operations. We have found that the quality of data used for training is very important, and it highlights the importance of AI-ready data, which has been mentioned. You know, we have high data standards, but it was the inclusion of the raw data and having the comparison of the raw data to the process verified data that made it complicated. So we did have to spend a lot of time still with data formatting, getting things set up correctly. And we are an authoritative data source. So we have to be able to explain how our data was inferred. It can be used in legal proceedings. We have to be able to defend those methods. So we think it's really important for if you're transitioning and you're an office like us, a federal agency, that you're very transparent. You publish we plan to publish the results comparing our existing methods to the AI methods. We're also exploring explainable AI methods as well as just AI methodology that is more easily explainable, is less black box. High performance computing resources, specifically GPUs, is really important. Especially once we really get to operationalize that, we're going to need to rely on those more. And we right now do not have an internal source of HPCs. We rely on our academic partners and things like that right now. The other main thing that we are also really concerned about is the loss of knowledge of our subject matter experts on this tied data. We think it's very important to still have a human in the loop and not make it completely automated, so that you are still retaining that knowledge base and knowing if the AI model is producing the results that you expect. And with that, I think you can go to the next slide. I can take any questions.
Perfect. Thank you so much, Lindsay. Yes, we do have a couple of questions already flooding in for you. From Jonathan Kellogg for the data shifts. Say it's something simple like a sensor being hit by a log and there's an adjustment to the baseline, but then the data are reasonable within that shifted time frame. Is there a vision to somehow calculate a correction and fix the shift?
Yeah, I mean, I think this is probably going to be dependent on the situation, but for us, so we go out to our stations like roughly every year, sometimes every 2 years, and check the elevation and check that everything's correct. So we have we have measurements of elevation of the station, of the sensor specifically at the station, every year, and we use those numbers. So if there's like a shift, that's how we compute it. We compute the elevation of the station 1 year, and then we do it the next after that shift, compute the difference, and apply a correction like that. That's how we do it now, but certainly you could apply some kind of correction just based on how the data shifted and how it looks too. But we do it as like an independent elevation measurement. So that's kind of unique for us, I guess.
Gotcha. And then another question in the chat from Alex. How can you decide on when the model is accurate enough? How do we account for the final percentage points of error when they get used?
So let me make sure I understand. So they want to know how we make sure the model is accurate enough. Like how basically, like how do we say like, okay, we trust this result?
Yes, I do believe that's what he's asking.
Yep, you got it.
Okay. So yeah, we're playing around with that. I did not talk about this, but that predictive score that kind of tells you like the confidence of the model with how sure it is if it's good or bad data. You can set a threshold with that. That's like, okay, only count it as bad if it's super confident that that data is bad. Like set it to like 80% or something, or yeah, 0.8. So that is how we think. We are still fleshing this out, and we, want to work with this closely with the postdoc. But what we think is we want to take a conservative approach and really focus on when the model's sure that it's bad, because again, we don't want to flag good data as bad and remove that from the record. That is a big concern. So we really want to focus on when the model's the most accurate, I think. And we still feel like at some level, there's still going to be some human review for us. but that comes to, the limitations of how much you can do with the AI model.
Yes, for sure. Yeah, if you have any other questions, pop in the chat in the Q&A. I was wondering, where do you see this model going in 5 years?
Oh gosh, the dream would be that, we have this running in our operations. We are now saving my team in particular a lot of time so that we can spend time really diving into like the issues more instead of doing the routine process that we do right now. I also hope that this is a useful tool for external partners and that we're able to support all of these all of these regional associations putting out low-cost water level sensors and can help be useful to them and can help them quality control their data more effectively as well. Basically, we want to revolutionize quality control water level data.
For sure. Take out all the human error. Okay. Thank you so much, Lindsay. I'll still just
Thank you.
Moment in case there's anything else that pops up. But again, you can just like throw in whenever you want. But to wrap things up today, we do have a couple exit questions for you, which will help us understand how building bridges can be most helpful to you in the future. So just like before, if you were with us in our previous sessions, we're gonna do a Menti poll. So you can go to menti.com or mentimeter.com. And we'll just get this up here for you. There we go. So yeah, you can go to menti.com, put in the code here, and then I will just hand it off to Alex, who's our AI training lead, to guide us through these exit questions for us.
Thanks, Jen, and thanks to all the presenters for some really interesting talks today. I think we've had a great survey of all of the really weird and wonderful and powerful and cool things that we can do when we start to engage with AI and when we start to engage with it right. We've got a couple of different Mentimeter questions. Feel free to use some of this time to ask questions to any of our panelists as well, because we still got about 10 minutes to go on that, and we're all still here. So use us while you got us. This is so if you can't get into the Mentimeter, we're not running it from Zoom, but you should be able to just go to the website from your laptop or from your phone and enter in the code there, and it should take you. For this first one, it's just actually it's the same question that we had right at the top of the very first workshop, and we thought it might be interesting to see kind of how that might have changed over the last couple of sessions. So it's just fairly simple association with how you are thinking about AI after the last 3 sessions and absorbing a lot of information. So I'll give you some time to fill that in. So impossibility, powerful. Clustering, problematic, for sure. Pattern recognition. Sorry, it's blocking off the bottom of the screen. Shen, how many responses do we have there now?
64.
Okay. Let's give it 5 more seconds and then we can head to the next one. Which I think the next one is just the word cloud that we ended up with from the very first session. So we can kind of compare how much space each of these ideas are taking up in your head between 2 weeks ago and today. Last time We were talking a lot more about efficiency and automation, future, chat GPT. So a lot of the same buzzwords that we're seeing in a lot of the media. Can we go back to the first one to see? And we're getting a lot more descriptive here. We're getting into a lot more of the kind of more complex concepts, some of the issues that are involved with that. So that's interesting to see kind of how your thinking is changing about this over the last couple of weeks. We can go to a couple of slides from now. Do we have any questions coming in for the other panelists? Not right now? Okay, that's all right. So the next couple of questions, we're just trying to get a better understanding of how your experience was with the last couple of workshops these past few weeks. So for this one, actually, I think most of the next couple of ones are open-ended. So feel free to take some time to type out some of your answer. For this one, after attending one or multiple sessions, what do you feel you have a solid or better understanding of? You got large language models. We didn't talk too much about those, except for some of the presentations this week. But I know that that's something that takes up a lot of cultural headspace right now. It seems to be very much everywhere. So that may be something that if you're interested in doing some specific stuff around large language models, that might be something that we could explore together too. Scope and capabilities of AI. Have a better understanding of the immense benefit that AI will provide to data collection and categorization, use cases, diversity. All right, that's good to see that we've learned some things in the last few weeks. We've gone through a lot of different content together. So I'm glad that some of it is hopefully making a little more sense to you. Why don't we head to the next one for now? So after the last couple of sessions, you've got a couple of things that are making a little more sense for you right now, but what are you still kind of having trouble figuring out or wrapping your head around? What's not quite making sense to you yet? We have some messages from the chat. If it's not working for you from the browser, maybe try refreshing it, or maybe try from your phone. Refresh worked, good. Thanks, Dwight. Ethics. Yeah, that's a big one. Technical applications, how you might use AI in your work, assessing model quality, what we're actually using AI for now. So hopefully that's a little bit clearer today, but yeah, for sure there's a huge world of AI and its applications. So there's lots to still kind of be baffled by there for sure. How to start with models, which models to use. What's new relative to classic neural nets? How to find skilled people. Yeah, that's a pretty universal one too. We've just got a couple of minutes left, so why don't we try the next question here? Or maybe give people a little bit more time. I don't know, up to you, Shen.
We can do one more.
Okay. After attending one more session, same thing. What are the biggest takeaways for you from the last couple of weeks? What's something that you think you might be able to actually use in your work, in your personal life, or even just something that you feel that is kind of more of a foundational way to think about AI, or something that is helpful for the way you look at it or think about it with respect to everything you've seen the last couple of weeks and everything that you're probably aware of in the wider world outside of this webinar. Cool things are coming, yep. Some cool, some maybe a little bit scary, maybe a little bit of both. Quality control for sensor data for sure. Having a better sense of examples of how we're getting to use this stuff. I think today's been really helpful for that too. Fully developed implementation we can share. So we had a couple of those that we talked about, but definitely some of the applications are a little more targeted, a little more narrow use. Use cases have been useful. The opportunities seem limitless. That's the problem, isn't it? Anyway, I'm gonna...
Yeah, I can wrap this up as more of these responses just start to come in. So thank you everybody so much for attending all of these sessions for Dive into AI. We hope you learned a little something along the way. We hope you enjoyed it. The goal of this first workshop series was really for you to gain a better understanding of artificial intelligence and how it might be used. And hopefully now you feel a little bit more confident with it. So in the coming weeks, you'll be able to find the recording of this and all of our previous sessions on the CU's YouTube channel. We'll also be circulating a summary report and an exit survey to all participants in the coming days. Please take 5 minutes to complete this if you can. It will really, really help us plan for future workshops and develop content that is relevant to you. The Building Bridges workshop series will be continuing in May 2025. So if you would like to stay connected, you can find us on social media, or you can email us at info@ceusatlantic.ca. You can also subscribe to our CU's newsletter to get any updates from there. So thank you once again for attending Dive into AI, and we hope you have an excellent rest of your day.